We're going to learn what the gamma special function is and why mathematicians care about it. The big idea is that it smoothly extends the factorial idea beyond whole numbers. Let's use a simple diagram to make the relationship easier to see. A great way to stay oriented is to ask, what problem is gamma solving? It's giving us a clean, consistent way to talk about factorial-like values even when the input is not a whole number. This is the main purpose of gamma. Here is the standard definition. You can think of it as a carefully designed area under a curve. The exponential part forces the far right tail to die off, and the power part controls what happens near zero. This integral is the definition of the gamma function. That condition, real part of z greater than 0, is there for a reason. Near zero, the power term can blow up, and we need it mild enough to still give a finite area. Far out to infinity, the exponential decay keeps everything under control. This is the convergence requirement for the definition as an integral. Now comes the key property that makes gamma feel like a factorial. We want a rule that relates one step up to the previous value. Using integration by parts gives a recurrence that shifts the input by 1 and pulls down a factor of z. This recurrence is exactly the kind of step-by-step rule factorial has. If we plug in whole numbers, it forces gamma to match factorial values, as long as we also know one starting point. This is the bridge from gamma to factorial. So, what is the starting point? Gamma of 1 equals 1, and then the recurrence builds everything else. That means gamma of 2 is 1, gamma of 3 is 2, and so on, exactly like factorial shifted by 1. This base value anchors the whole recurrence. Here's where gamma becomes truly special. It gives meaningful values at half integers. The famous one is gamma of 1/2, which equals the square root of pi. And then the recurrence lets you get gamma of 3/2, 5/2, and so on. This is the classic half-integer value. Even though the integral definition started with a restriction, gamma can be extended consistently to almost all complex inputs. The only places it fails are the non-positive integers, where it has poles, meaning it blows up instead of giving a finite value. These are exactly where gamma is not defined because it has poles. One of the most useful identities is the reflection formula. It connects values at z and 1 minus z, and it explains a lot of the symmetry you see when you graph gamma across the real line. This right-hand side controls where gamma must blow up. Gamma also packages nicely with another special function called the beta function. This relationship is powerful because it lets you convert certain integrals into products and ratios of gamma values. This ratio is the standard connection between beta and gamma. Finally, to understand how gamma grows, we use Stirling's approximation. It tells you gamma grows extremely fast, and it's the reason factorials explode so quickly too. This part shows the dominant growth behavior.